Hi, this is Rohan from Educator.ai. Let's dive in. Let's build a clear mental model of two ideas that quietly govern everything a large language model does. The context window, which limits how much text the model can see at once, and the KV cache, the trick that makes generating that text fast. By the end, you'll know exactly what fits, what gets recomputed, and why it matters for your code. Here's a puzzle every developer hits. You paste a long document, ask a question, and the model seems to forget the start. It isn't broken. A language model reads text as a sequence of tokens, and there is a hard cap on how many it can hold in mind at one time. Understanding that cap explains a huge amount of odd behavior. A token is a chunk of text, often a word or a piece of one, that the model treats as a single unit. Before anything else, your text is split into these tokens, each with its own numeric id. This matters because the model's memory limit is measured in tokens, not characters or words. So the very first step is turning language into a list of numbered pieces. Think of the model as working at a desk that can hold only a fixed number of cards laid out in a row. Each card is one token. As long as everything fits on the desk, the model can look at any card while writing. But the desk has an edge. Push in new cards, and the oldest ones slide off and are simply gone. That edge is the context window. The context window is the maximum number of tokens the model can attend over at once. Crucially, it's one shared budget. Your system prompt, the user's question, and the text the model generates all live inside the same window. If the model writes a long answer, that output eats into the same space as your input. Cross the edge, and the earliest tokens drop out of view. So what does the model actually do with those tokens? At each step it runs attention. Every token looks back over the earlier tokens and pulls in the information it needs. Here the word Matt is attending. It leans heavily on cat, tying the scene together. Notice it only looks backward at tokens already on the desk. This is how context becomes understanding. Let's peek one level deeper. For every token, the model computes three vectors: a query, saying what this token is looking for, a key, advertising what it can offer, and a value, the actual information it carries. A token compares its query against every earlier key to get scores, then blends the values by those scores. Keys and values are the memory of the past. Remember that, because it's the whole point of the cache. Now, the performance problem. The model generates one token at a time. To produce the next token, it needs the keys and values of every previous token. The naive approach recomputes all of them from scratch, every single step. But those past keys and values never change. Token 1's key is the same, whether the sequence is 3 tokens long or 3000. Recomputing them is pure waste. The fix is the KV cache. After computing a token's key and value, the model simply saves them in memory. On the next step, it only computes the query, key and value for the one brand new token, then reuses everything stored. So instead of redoing the whole history each step, it does a tiny bit of new work and looks up the rest. This is why generation stays fast token after token. The cache saves recomputation, but it can't cheat physics. Each new token still has to compare its query against every stored key. So the more tokens in the window, the more comparisons per step, and the more memory the cache holds. That's why long context feels slower and cost more. Attention work grows with sequence length. The window is a budget on both memory and speed, not just how much the model remembers. Let's make this concrete with a simple count of operations. Without a cache, each step rederives keys for the whole sequence, so its cost scales with the square of the length. With a cache, each step only adds one new key and compares against what's stored. Run it. Even at just 8 tokens, the cached approach does far fewer operations and the gap widens fast as sequences grow. Here's the check you'll actually write. We tokenize the prompt and the notes, add up the input, and then this is the part people forget. Reserve space for the output the model will generate. Both input and output share the same window. If the sum exceeds the limit, the request either errors or silently drops your earliest tokens. Counting tokens before you send is the habit that saves you. 2 myths worth killing. First, the KV cache does not increase how much the model can remember. It only avoids redoing work. The window limit is unchanged. Second, The output doesn't get a separate budget. It competes with your prompt for the same tokens. And when tokens fall off the window edge, they're gone from the model's view. It isn't quietly remembering them somewhere. Here's your review lens. On the left, the habits that keep you safe. Count tokens upfront, reserve space for the answer, trim or summarize stale context, and respect that a long window costs both memory and time. On the right, the quiet failures, guessing token counts from character length, forgetting the output competes for room, expecting fallen off tokens to stick around, and believing the cache grows the limit. It doesn't. So 4 things to carry with you. The context window is the maximum tokens the model attends over at once. Your prompt and its output share that single budget. The KV cache stores past keys and values, so each step only computes the new token, keeping generation fast. And because every token still compares against all the rest, cost and memory grow with length. Design your prompts with that window in mind.